Okay, how about we do this one? This is clearly an energy problem because it has a spring. No, just because it has a spring does not mean that this is an energy problem. You have to ask yourself 3 questions. Okay, let's ask them and find out if this is an energy problem. 2 kilogram collar attached to a spring that has an unstretched length. This collar is drawn to point B, released when rest, determines its speed when it arrives at A. Ready? Okay. Is it a time spanner? Yes. Okay, good. Is it, do I care how long it takes to get to point A? No? Okay. Then let's see if I can get all the works. So what I'm going to do is I'm going to list out all the forces and we'll just check them off one at a time. Okay. There's a gravity. There's a normal from the rod. There's a spring. What else is there? Anything else? Okay, let's go through them one at a time. Are you worried about gravity? No, I got a potential energy. Not worried about him. How about the normal? Any work done by the normal? No. And why not? Well, yeah, there's no friction, right? But he's not even listed. But why does the normal do nothing? Because he's perpendicular, right? He doesn't try to speed you up. He doesn't try to slow you down. He just simply tries to hold you onto the rod, right? The normal doesn't speed up, slow down. So there's going to be 0 work. He's perpendicular to the motion. So I'm not worried about him. What about the spring? Are you worried about the spring? Don't say yes. I see you nod. No. You're not worried about the spring. Why? Because I have a potential energy. I don't worry about anything that has a potential energy. Now, if I want to do it the hard way, then yeah, I worry about it. I'm going to do it the easy way. I always do it the easy way. I suggest you do it the easy way. You've got a potential energy for spring, then you don't worry about it. You just shove him in there. Okay, here we go. Is it an energy problem? Yes, it is. Okay, let's use energy. Okay. So, energy in minus energy out equals change in energy. You got any energy going in? No. Well, the spring. You've read the first part of the chapter, and that's where he's calculating the work of the spring, and man, that's hard, that's complicated. I don't do that. You can either use the work of the spring, or you can use the potential. Don't use both. You can use the work of the spring, or you can use the potential of the spring. Don't do both. They're both equal, but don't do them both. Right? Just like gravity, you can put the energy of the work of gravity, or you can take the potential energy of gravity, but not both. Got it? Do the easy one. The easy one is to use the potential. Now, if you just want to prove that you got guts, okay, do it any way you want. But I recommend you do it the easy way. Use the potential when you got one. Smoke them if you got them, right? Go for it. Okay, so here we go. Any energy in or out? No. No. Spring? No, I'm going to use the potential for the spring. No. Okay, 0 equals what? Final minus initial. Okay, here we go. Here comes the final. How much energy do you have when it gets to A? Does the mass have any energy? Is he moving? Okay, then he's got kinetic. So let's put it in. 1/2 mass times v squared. Does he have any gravity? Kind of depends on where you choose 0. Where do you want to choose 0 gravity? Right, yeah, at the center of mass, I'm going to select that rod AB. So we'll say, okay, right along here, this is going to be 0 gravity. This is gravity, energy equals 0 right there. So do you have any gravity energy? No, okay. Any other energy in the mass? Spring. Okay, let's get the spring. So I've got some spring energy, 1/2 K. What's the squish when it gets back there? How long is he? Yeah, he has an unstretched of 2. How long is he now when he gets to A? He's 5 when he gets to A? Looks to me like he's right here. When he gets to A, there's the spring right there. How long is that? 3? Okay, so
How much is he squished? Well, he's 3 now. When he's unsquished, he's 2. How much is he squished? 1. Watch the units. Squared. The squish is not 3. The squish is not 2. The squish is, he's 3 right now. If you leave him alone and don't touch him, he'll be 2. Well, then you must have pulled him 1. Make sense? That's where you're going to mess up on energy, is right there. Okay?
This is where you're going to mess up on it. Oh, you didn't miss it. How long is he when he gets to A? He's 3. You can see that in the picture, right? The problem statement says that unstretched, free length. If you leave him alone, he's 2. If you don't push him, poke him, do anything to him, he's 2. So how much have I stretched him? He's now 3. When you leave him alone, he's 2. Well, what did I do? I stretched him 1. 3 minus 2. This is how long he is, 3. This is how long he is at the free. So it's going to be, how long is he now minus 3? Make sense?
Okay. Anybody else got energy at the end? Don't think so. Minus. Let's get the beginning energy. Do you have any kinetic energy at the beginning? No. Do you have any gravity at the beginning? Do you have any spring at the beginning? Yeah, okay. Plus 1/2 K. Let's see how long he is or how much he's squished now, right? So he's a distance of 5 right now, minus 2. So I've stretched him 3. So this would be 5 minus 2. Watch the units. I don't know what the units are, but watch them. No forgiveness for not watching units. How many unknowns? How many equations? Bingo. Okay. Trivial, right? See how simple they are?